I'm just going to take you through looking at some pictures, some stories, and then drawing the free body diagrams appropriate. I'll set them all up in the abstract and we can talk about how you would solve them given the numbers, but the most important skill is realistically being able to draw the free body diagram first and then base the equations off that. So for something like this is like pushing a box into the ground or pushing a lawnmower. In any way, you're pushing it to the right, but you're also pushing it down. The free body diagram, again, the free body diagram is just the forces. So we have the normal force, we have gravity, we have an applied force that's a certain angle below the horizontal, and then we have friction on the ground. In this particular case, it's not really a system, it's just looking at that one block. And so for this particular one, we'll do an x hat and a y hat. In the x hat, it's really no more than saying F equals ma, and just doing the right forces minus the left forces. So the forces that are to the right are Fa times cosine theta minus the force of friction, and that equals ma. If the applied force horizontal component is bigger than the force of friction, it will cause that mass to have an acceleration. If these two things were equal, this would be equal to 0. If you were looking for the applied force just to make it move, like just to overcome friction, you'd still set this equal to 0, and that'd be fine. In the vertical direction, we have the normal force that's up. And when you're pushing a lawnmower, you're actually pushing it into the ground. And so you have to subtract Fa sine theta, and of course subtract the gravity for being down. And that's equal to 0 because we know that there's no acceleration in the y direction. So that means we know there's no net force in the y direction. And the typical song and dance is that we're going to use that equation to solve for the normal force. And in this case, you can see that the normal force is bigger than gravity because you're shoving down on the block. So you're shoving down plus the weight of gravity. The normal force has to respond to both of those forces. And then we can use that up here because we know that the force of friction is equal to mu times the normal force. So in this particular case, we know that the normal force is mg plus Fa sine theta. So really the x equation becomes Fa cosine theta minus mu times mg plus Fa sine theta, and that equals ma. And at this point, one of these is a variable. Maybe they say you just want to make it move, so you set the acceleration equal to 0 and you find the coefficient of friction, or you find the applied force that makes it move. But realistically, the free body diagram leads you to these equations. We almost always want to know what the normal force is for this particular problem because we need to use the normal force in the friction equation because friction is mu times the normal force. And then after this, you can solve for whatever variable you want based on the different situations. Okay, this one, let's push an applied force that's up and to the right, certain angle with respect to the horizontal, a block that's on a wall. Okay, so let's find out the maximum F such that it won't move. If we push any harder than its value, it'll accelerate up. And so if we draw the free body diagram, we have mg down, and if we really want to push it really hard up, well, then friction is also going to be down. The applied force is up and to the right, and then we have the normal force, which is the wall pushing back on the block. In the x direction, we have Fa cosine theta, the horizontal component of our force, minus the normal force equals to 0. And why is it equal to 0? Well, when you push this against the wall, there is no acceleration in this direction, and so that's equal to 0. In the y direction, we have Fa sine theta, right? Our vertical piece pushing up, it would be this piece in the picture. And then mg is going down, and then friction is going down. And then if we were looking for the maximum that it would just barely, not move up, we're still going to set the acceleration vertically equal to 0. Now, if we were pushing it hard enough that it was accelerating up, then we would put ma here. There's never going to be acceleration in this direction unless you push it hard enough that you can topple over the wall. And the same idea. We're going to use this equation here to solve for the normal force. So the normal force is equal to Fa cosine theta, and then we can use that in the bottom equation and say that Fa sine theta minus mg minus mu times the normal force, but the normal force is Fa cosine theta equals 0, and then we have this equation, and again, any one of those things could be variables. But picture, free body diagram, in this case an x and a y hat equation, anytime you have a single block, it's probably important that we look at both the x direction and the y direction, and then we can solve for the normal force. Again, the normal force in this case is Fa cosine theta, and we can use that to substitute in for the force of friction. Okay, let's say we were solving for the min and max of this m, okay? So the maximum of capital M. Well, again, we're not really going to do x hat and y hat because this horizontal direction has everything to do with this vertical direction. That's the function of the pulley. It changes this vertical motion into horizontal motion up here. And so this, we'll just start out with F equals ma, like we always do, and think about what are the forces that are making this system move. Well, the acceleration is going to be in this direction. And so we have this one's weight, mg minus, now this, if you drew a free body diagram for that one, it would have m1g down, a normal force up, a tension to the right, and a force of friction this way. If you drew a free body diagram for the hanging one, you'd have capital mg down and some tension up. Okay? The string doesn't provide a force to the system, it just connects the boxes. Realistically, this mg is balanced by the normal force, right? The table balances the weight of this one, but this friction, mu m1g, does oppose the motion. And I know it's just mu m1g because I know in this situation the normal force is directly balanced by m1g. And that equals m1 plus capital M times A. Now if we're looking for the maximum it can be so that it doesn't move, we still are going to make that equal to 0. And we solve for that value. Okay, anything bigger than the value we find, then this weight will be bigger than the friction, and if the weight's bigger than the friction, then it's going to accelerate this way. Anything less than that, let's say we find capital M is, 5 kilograms. Then anything bigger than 5 kilograms, it's going to accelerate this way. Anything less than 5 kilograms, and it stays stationary. Of course, it's never going to go in the opposite direction because there's no force able to lift this, because there's no force going the other direction. Okay? Okay, let's look at a 3-block system. Again, when you look at the system first, the total system, the only force making the system move is Fa. Now, if there was friction, then you'd have to subtract friction from this one, friction from this one, and friction from this one. But on these types of situations, they typically don't include friction. Okay, so let's just say there's no friction on this one. And so the only thing making the whole thing move is Fa. And what does it do? It makes all of them move. Right? The net force is responsible for making the entire system have a certain acceleration. So then you'd find the acceleration. If I told you that, all of these were, this was, let's say 2, 3, and 4, and you had an applied force of 18 newtons, these were all in kilograms, this is just 918, and you find the acceleration is 2 meters per second squared. Well, if I wanted to find T1 and T2, I just look at just M1. So if you just looked at M1, well, T1 is the only thing making M1 move. Well, what does T1 have to be? Well, if M1 was 2 and the acceleration was 2, you know that that's got to be 4 newtons. If you looked at M2, well, T2 is making it move, but T1 is pulling back on it, and it's that difference that causes M2 to move. But what's T2? Well, you know that's 4, and you know this is a mass of 3 and acceleration of 2. That means that T2 has to be 10. That's 10 newtons. You could check on the third block. If you just did the third block, it'd be the applied force is trying to pull the third block, but T2 is pulling it back, and that causes M3 to experience a certain acceleration. And all of this will just check out. So we'll have the applied force was 18. We already said T2 was 10. M3 was 4, and the acceleration was 2, and look, you get 8 equals 8, meaning M3 is consistent with the values that we already found looking just at M1 and just at M2. And again, these equations came from the free body diagram. If you looked at the free body diagram for M1, you'd say T1, normal force, and M1G. These are totally balanced, and the only thing making it move is T1, and there's no opposing force. If you look just at T2, you'd have, M2, you'd have T2 pulling it to the right, T1 pulling it to the left, a normal force going up, and its weight going down. And again, balance here, and the difference between the tensions in the string causes the second mass to experience a certain acceleration. All consistent. All right, now when we look at the ramp situation, again, you're not really sure what direction it's going to go. If m2g sine theta, this piece of gravity is big enough, the whole system might go this way. If m1's weight is big enough, it might go this way. Let's say that it's going to go this way. Okay? And again, we'd have to look at the actual values for m1 and m2, mu and theta, to actually make this decision. But let's say it's going to accelerate in that general direction. And so what we're going to do is we're going to look at the system in general and look at F equals ma. What are all the forces making the system move? So we have this one's gravity, this direction, m2g sine theta. You have the friction of this block going in the opposite direction, which is mu m2g cosine theta. And again, previously in the video, we've talked about how to do the ramp, but again, if you need to do the ramp again, there's mg, this is some theta, this is the gravity down the ramp, and this is into the ramp. If this is theta, this is some alpha, those angles are the same, so that corner angle is theta. But if that's theta, this is the opposite side, so that's mg sine theta, and this piece is mg cosine theta because it's adjacent to that angle, and that's why this piece balances the normal force. So the normal force is that way, and mg cosine theta is this way. Mg sine theta is the one down the ramp. And so we have down the ramp, the normal force, so the frictional force is mu times the normal force, and then this guy's weight, m1g, that's the net force on the system. That's making it go. Both of those forces are opposing that motion, and that causes the system, meaning the total inertia of the system, to experience a certain acceleration. As you can see, the tension is certainly there and there, but it's an internal force. The rope just connects the blocks. It doesn't add any net force to the actual system. If you wanted to find the tension, you could look at the hanging block and say, well, that's tension up, m1g down, and so T minus m1g equals m1a. Once you use this equation to find the acceleration, you could use this equation to find the tension. You could have used this one, but the hanging one will be easier. And again, I knew to say T minus m1g because I know the tension is greater than the weight. If the tension was less than the weight, then the thing would be accelerating in that direction. Okay? And the last question. So we have like this double ramp scenario. Again, you'd have to really look at of whether m3g sine theta or m1g sine theta is the bigger force here. Let's say the whole thing is going to go this direction. What we're saying is that m1g must be much, much, much bigger than m3 because we're going to have a whole bunch of friction opposing the motion, and that only really one thing is driving it. So when you look at the system, F equals ma, you're going to take m1g sine theta, that's the weight of m1 going in that direction, and that's the only force that makes this whole system move. There's no applied force, it's only this one's weight down the ramp. And again, m1g sine theta is down the ramp. And we have to figure out all these other forces that are opposing it. So let's just work left to right. The friction on m1 is mu m1g cosine theta. The friction due to that one is mu m2g. Now remember, there's no angle there, so the normal force on m2, again, if you did the free body diagram for m2, you'd have m2g down, normal force up, T2 that way, and T1 that way. Okay, the tensions don't appear in the system equation because the ropes don't do anything other than connect the blocks together. So we have this one's friction, and now we have this one's friction, which is minus mu m3g cosine theta, and we have this one's gravity, minus m3g sine 2 theta, and that equals m1 plus m2 plus m3 times a. Again, this would have to be a really, really, really big force because it has to overcome friction, 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 and the weight of this. If you do this and you get a negative number, number one, you either picked the wrong direction or it didn't move. And realistically, to figure out the direction, Just look at m1g sine theta versus m3g sine theta 2. Those are the two weights, the weight of this one versus the weight of this one. If this has a bigger weight down the ramp than this one has down the ramp, then this is the right guess. If you do this whole thing and end up with a negative, the only conclusion is that it doesn't actually move. Okay, and so we started out knowing that m1g sine theta was bigger than m3g sine theta 2. And if that's true, then this will either be a positive, it'll be 0, but if you get a negative here, it means that the whole thing doesn't move. None of the weight differences was enough to overcome the friction, and the whole thing would just stay stationary. Okay? Normally, though, this would be big enough to find an acceleration, and so you'd use that, and you'd find some acceleration, and then you could find the tensions again looking at the individual boxes. You could look at box 1 and say m1g sine theta minus mu m1g cosine theta minus t1 equals m1a. Again, I'm doing the free diagram just for that one. You could look at box 2 and say what we set up here. T1 minus mu m2g minus t2 equals m2a. And you could look at that box. Or you could look at box 3 and say t2 minus m3g sine theta minus mu m3g cosine theta equals m3a. Again, tension up the ramp, gravity down the ramp, friction down the ramp. That net force is causing M3 to accelerate. On the top, left rope, friction, right rope. The friction and the right rope are causing it to slow down. T1 is trying to accelerate to the right. That difference is the net force on M2A. And again, once you find these accelerations, then you can find tensions. I did say in class something about so like D equals 1/2 AT squared. And, if you knew that you needed M1 or M2 to go a certain distance, well, once you know the acceleration rate of them, again, of them, meaning all three of them have the same acceleration rate, and you know a distance that you want them to go, you can easily use that to find the time. Or you know the thing was in motion for 2 seconds, and you know the acceleration. Then you know how far it's going to slide. And this distance down the ramp is the same distance as this would slide horizontally on the ramp, which is the same distance as this would go up the ramp, because they're all connected by a rigid string, meaning it's not going to stretch or anything. So all of those things have to be connected. You can even find out velocities. If you look at the v² equation, if you wanted to find the velocity after moving a certain distance d. If you move a certain distance d and accelerate, and you don't start out with anything, then you can use the v² equation to find out like the velocity m1 would have at the bottom of the ramp if it slid down a distance d. Again, you don't even need the time. You can just go straight to the v² equation to relate the final velocity to an acceleration. Again, the acceleration was found by the analysis of the force equation, and then if you tell me the distance of acceleration, I can tell you the final velocity. Hopefully this helps you study for your test, and if not, take a look at all the book problems, the multiple choice. They're all very similar, but you absolutely have to be able to write free body diagrams for equations, and then use the idea of looking at the system equation to find an acceleration, and then individual equations to find specific tensions and such.